All right, so it says it's 11 o'clock, so it must be time. On the wiki, there's a zip file with a couple of things in there. So everything I'll show is in there. So what I'm planning to do is just sort of walk you through some of the exercises or tutorial exercises, whatever you want to call them. Bill started last week with a number of applications where the idea is you sort of see how isotopic values or ratios change over time. And we had one model left, so we did a couple of different exercises with that already. We had one model left where we were trying to mix some material back in the mantle and then wanted to see how that would evolve. So I've taken his Excel file and tried to put everything on one sheet so that it's a little bit more obvious what you can play with and how it will affect things. So we'll do that. And then the second part, I'll spend some time trying to show you or let you play with mixing of things. So in the end, this is the kind of stuff we're trying to explain. And the way you have to explain the isotopic data is you have two options. You can think about it as a effective ingrowth, radiogenic ingrowth, or radioactive decay making for radiogenic ingrowth of some of these isotopes. Or you could take two different things and mix them together and get mixed compositions. And so usually when you have a data set, in the end that is the two big things you can think about in terms of explaining your data. Here I try to sort of make this obvious. So this is what we were doing last week effectively. You start with some composition that we think might represent the entire planet, and then at some point you make two different things. You make some sort of melt. This is in this case the neodymium system. So at some point in the past you make a melt that has its evolution over time, and we have whatever's left from the melt, which has its own evolution, because the parent, the radioactive parent, is split from the radiogenic daughter when that melting process happened. So if you end up putting a lot of samarium, the parent, into the residue is going to have a lot of samarium to generate the radiogenic daughter 143 neodymium. So that grows in really fast. If you take most of the samarium out of, or don't put it into the mantle melt that ends up making the crust, then that's not going to really grow in a whole lot more neodymium, so this flatlines a little bit more. And so in the end, all you're trying to do is come up with an explanation for here and here at time zero, at time now. How do I get crust over here and mantle over here? And so you have to play with when in the past did you split them apart, and how steep are these two curves, which depend completely on this fractionation here. So you did on, I forget what day, last week we did this. You've done some calculations of how this evolves. We did a crustal component that was being extracted. The one that we haven't done yet is, okay, what if some of this crust goes back into the mantle, mixes back in? And so that's what the component is that's left. So we'll play with that for a little bit first, and then after that we'll do a mixing exercise. So as I said, on the wiki I put a zip file that has it has two Excel spreadsheets in there. One is an updated version of what Bill gave you. So what I did is on the top left of the spreadsheet, let me try, I forget what I called it, let me see. So that's this one, CIDER Tutorial Geochem 2 version 2. So I put all the variables in this box here. And so the goal is basically you have two things we're trying to make. We're trying to make a mantle component and a crustal component. So there's a blue dot and a red dot. And the whole idea is to see how changing some of these variables, how that affects where the end points are. So these endpoints here are just how this and this ends up happening by changing how these variables change, samarium to neodymium elemental ratios, so that's in the effective partitioning. The recycling efficiencies, how much are you sticking back into the mantle, and how much is the total mass that's being recycled. These are all the variables basically. And then besides that, there is the initial condition, the original point that you started with in this map. Like, do you want to start here, or do you want to start a little higher, lower? Left, right is also an option if you think about what we did last week. We said the age of the solar system we know quite well. The Earth probably, as a solid body, probably started a little bit later, so you can also shift that around a little bit. And so all that's now wrapped into here. So basically what you want to do, and that's sort of the exercise here, is to try and play with all the numbers in red to see how that affects where the blue dot and the red dot are. So I wrote down a few things up here that you should think about is how does changing this number or these recycling efficiencies, how does that affect where these two dots are? And then in this plot, this is just one plot. This is strontium versus neodymium. In the spreadsheet, let's see here. So in the spreadsheet, I also have another plot next to it with 206, 204 lead and 207, 204 lead. So this is where the majority of the mid-ocean ridge basalts and the ocean island basalts plot. This is where the crust plots. In the lead plot, you're seeing lower crustal zenith. This is continental material mostly. Here's some upper crustal stuff. The blue field is the mid-ocean ridges, and then the yellowish field is the hotspot oceanic basalts. So basically what you have to do is you have to find values here that will put this blue dot in here, put the blue dot in this field somewhere, and the red dot needs to be in the continental crust. This red dot right now is actually quite below where the continental crust roughly would be. Right? So that's sort of the idea, is what do you have to do changing these numbers around to get these dots in the right place. That's basically what you're trying to play with. So I'll let you guys play with that a little bit, and as I said, the things that I'd like you to look for are these things here. So what is the effect of changing these recycling fractions, and what do you have to do to make the red dot in the lead field actually work out? Because right now the crustal lead in this model is up here right now, predicts that the crustal lead is down here, but if you look, crustal lead is all up here, so there's something not right in this model yet, right? So red is for the crust and blue is for the mantle. What's that? Kind of both blue?
Yeah, it's two light blue. That's quarter.
Oh, you're talking about the little cross?
Yeah.
That was already in the image behind it.
Yeah, that thick red little cross is the average of mid-ocean ridge basalt. So ideally, if you could get that.
That would be really nice if you could get it there.
But you're going to have a lot of trouble getting that right.
So, I think what Sana is saying is that in the version we have both the blue square and the red diamond are in fact pale blue, but there's still a square and a diamond.
Oh. Yeah, something funky happened last night when I was trying to put this all in a zip file. I'm not entirely sure what happened or what. When I looked at my version, it still looked okay, but maybe something is still not quite the same. So yes, look for the diamond versus the square, I guess, if it doesn't look red and blue. I think it also might have to do with your version of Excel.
Look, it's ugly.
Yours is purple.
Yeah.
Wow.
But at least this is red.
Yeah.
It's so
Yeah.
weird. Look, her color's different.
Oh, you have pink and red. This is nice.
Who wins?
Yeah, that's right. Who's got the golden ticket? All right. Well, mine is gray. Your colors may vary. Yeah, maybe.
I made it green.
Another thing to note is I sort of put a reasonable range next to it, but that's actually just mostly reasonable so that the dots don't go way off the plot. Reasonable range could also be thought of as we think that partitioning of lead or rubidium or whatnot can only be in this particular range, and that might actually narrow it down a little bit more. So when you play these games, you may be able to make it work, but then you would actually have to go back and check, okay, how did I make it work? Can that actually work that way? Is it realistic to have this much material move from the crust to the mantle?
Remind me what the efficiency factors are versus the D.
Put it on the side. Yeah, there you go.
So there's the mass to crust flux.
This is just a total flux.
Mm-hmm.
So the recycling efficiencies just basically per element say, okay, how much is actually moved back into the mantle. So this is basically separating total mass going into the planet again from how much in that subduction zone is actually sticking with the slab versus leaving.
Oh, so that's the crust to mantle fraction.
Right.
Ah,
And
okay.
this is when you're making the crust, how much goes into the crust. This is while you're destroying the crust, how much comes out and sticks with the crust versus how much goes back into the mantle.
Okay. I'm going to rename those things in my spreadsheet. It's mildly confusing to me.
Yeah. No, I left the names that Bill had in there.
Yeah.
So that way we have a direct link to the write-up he did.
Okay, thank you.
Mm-hmm.
Jasper, the blue square in the tranche
always
of
not there.
neodymium plot, should it be as far up as possible, or like it's more
So
of the most depleted?
Morbus, basically it, right? So that's about as depleted as it gets, and
Okay.
so
And so I just have to push it left.
you want to get it to go to the
Okay.
left more,
Sure. As much as possible.
but within, like towards the top of the field, not outside of it, probably too much.
Okay.
Has anybody made lead work yet?
Well, there's an interesting issue with lead also, which is that the recycling efficiency of uranium and lead might be very time dependent and not constant.
Right.
Because of the uranium solubility is redox sensitive.
Right, the redox sensitivity, that's what Bill was already mentioning earlier. That's one issue with this, is that this assumes just a time stepping process that stays the same throughout the history of the Earth. But what I get, like I was trying to do that just now, every time you change one, you can get one to go up, but then the other one wants to go down. And so if you want to get the blue up in the Morb field and the red up in the Crustal field, that's a really hard trade-off to hit just right. Having a fun time.
Yes, thanks.
I don't want it over there.
See, look. It's like
Yeah, yeah.
saying,
Now you just gotta close up the gap a little.
but I don't know what. None of these actually moved it. Anyway.
None of them moved it what?
They only go up and down really. They don't
Yeah.
change.
That's because they're basically, that's where it ends up from radiogenic ingrowth. They're both lead isotopes, and so you're growing in along a curve, and it's fixed when they split, and so all you're changing is up and down a little bit. They're not going to move too much in this direction at all because it's mostly age related where they end up. So there's a reason why the lead always stays on a line effectively. Basically what you're doing, this is a lead evolution of the Earth plot in the two same isotopes that you're working with. So if you start with 0 here, is an iron meteorite from Arizona that has basically no uranium in it. So the lead in there is basically what we started with. That evolves over time like this, and then you pick some time in the past from where you make melt and a residue mantle, you get these sort of superimposed curves off of the original curve. And based on the age where this happens, you end up with two dots that are growing in from that time forward, and they end up on a linear relationship that's based on the age. It's because 7 and 206, 207 lead are both a uranium daughter, and so their ingrowth is coupled because they're the same uranium to lead system, just with different half-lives, which ends up making this curvature. So because of this, you just have two dots that are basically stuck on a line that's determined by the age where the split happened. And you're basically just moving things along here based on the uranium to lead ratio. So you're sort of moving things along a line, more or less. Yeah.
This figure's a little weird because it goes from -20 to -30. It's supposed to be 5 increments.
Huh. Yeah, how about that?
I just want to double check, make sure these were lined up.
They were lined up by +15 to -30.
Yeah, I was just double checking.
Yeah, they're off a little. The bottom line ends up being, I mean, the crustal field is really huge. We have no idea exactly what's what.
Right, so the question is, should that actually be -25?
It probably should be, yeah. I don't know. Actually, this came from, I don't know where Bill got this from. It may be intentional that it goes and skips. But yeah, I should have looked at that a little harder, making it fit. Although in the end it doesn't matter too much. But. Yeah, Curtis brings up an interesting point. The scale lobe runs from 15 to 20 to 30. So there's a hop of 10 all of a sudden. So the plot that I lined up lines up with plus 15 and minus 30, so it's not exactly right. In the end, in the big scheme of things, it doesn't matter too much because where that red dot ends, as you can tell, doesn't matter all that much. If it's somewhere in that lower half, you're pretty much good. But the point is, this doesn't line up perfectly. All right, so what's the effect if we change? So I put my dots in a not quite reasonable, but close to reasonable place. What happens when we change the efficiency at the top there? That 0.5 value, the recycling fraction. Anybody tried it yet? Moves things up and down. So what shall we try? 0.25? So all of a sudden red's gone. Blue comes down a little bit so it's not as depleted anymore. Lead doesn't seem to care quite as much. No.
How low can the continental crust be in epsilon neodymium?
How low can it be in epsilon neodymium?
Can it be minus 50?
I don't think so. I don't know. Bill, do you have any idea how low the continents can go in epsilon neodymium?
How low the
Continents. I mean, yeah. Bill has spoken with minus 30. I mean, you could look for really old crust and see if you can find a lower value. Maybe some of the Archean stuff has lower values. I'm not sure.
when I was trying to get the tutorial set up, it looked like maybe something like approaching minus 20 was a more reasonable.
Yeah.
But it's not very well constrained in particular because we don't know the lower crust.
Yeah.
We have fairly good constraints on the upper crust for our separations, but the lower crust is hard to constrain.
Right.
Yeah, and obviously it's sort of an oversimplification because we haven't taken into account any intracrustal differences.
Right. Right. So that was going to be my next point before we move on to the next exercise. So particularly in the lead, it's pretty obvious. So we're able with this simple model to make two dots on the map, right? We put a red and a blue dot on the map. But then if you look at where the fields go, clearly there's got to be more going on in the planet than just crust and mantle because we have lower crustal xenoliths to the left, we have ocean islands back to the right and up a little bit. So clearly we need a more complex model to explain all the data, to explain all the scatter. And so that means introducing more than just making some continental material through time and recycling it. We need oceanic crust made, and we may need a fair bit of work done inside the continental crust to sort of explain the ranges that you get both within the inside the lower crustal xenoliths. So this is our best guess for what the lower crust might be, is whatever we pull out of xenoliths that come out of the volcanic systems on continents. So that's rocks like the pictures you saw in Brad's talk this morning. And then this says marine sediments and upper crust. The idea is that if you go walk up the hill here, you'll come across a whole bunch of different rock types. It's hard to go through and sample all those and measure them all. You can use nature's way of sampling that and just basically measure the composition of the sediment, which sort of averages it all out. And so we like to use the sedimentary averages as an estimate of what the crust could be, the upper crust could be. So that's that field. And so obviously you need, besides splitting a crust and a mantle, you need to do a fair bit more work to get this sort of scattered, this sort of range in isotopic compositions. Has anybody made an exact match yet? Got it all to work? And
the more the easy, but the continental crust is hard.
In the lead, yeah.
What's the target for the continental crust? Like, the hole in that green block, or the upper I can get it, the better.
So this is lower crust and upper crust. So if you can get it in that field, you're good. So in this case, you have it within more for the depleted mantle part, and then you have that inside the crust. So that's probably okay.
It should be within the values of the reasonable.
Yeah, I mean those are kind of guesses. As I said, I mostly modified that just to sort of keep the dots within the plot. You could spend more time to actually say, okay, this is not really reasonable to have the rubidium versus strontium be that far apart. You can actually go back and say, okay, now I've made it work. Are these reasonable estimates for how much material is moving from one side to the other, or how much rubidium is moving into the crust and back into the mantle?
So yeah, I mean, yeah, what I mean, shifting.
How hard is this range that you're giving us?
Which range?
Like if I say the lead effective partitioning is 1.4 instead of 2.7.
Oh, I just played with those numbers a little bit to sort of keep the dots in the box. The idea is, like, if you can make it work with another number than what I had there, this was just to sort of make you not lose your dots. But what you would have to do is go back and actually, once you've made it work, you'd want to go back and say, is it actually reasonable that this much lead goes from one reservoir to the other versus the uranium?
Another experiment you can do fairly easily in the spreadsheet is not set up to do it, but it turns out you can do it fairly easily, is to delay the crust and mantle recycling. And the way you could do this, say it's set up to start at what, 4 point, right now it starts at just 4.417. But if you simply if you wanted to start recycling in 3 billion years, you could simply copy the line above that down, because the first line of crust production doesn't have that there. So you just copy that down further all across the board.
So you have up to here, you don't have any crust yet, right? So this is where crustal growth starts, basically at this step, and then I think you have the recycling starts the next step. Is that right? I forget.
I think it starts. Yes.
Yeah, here it is. So you can just take this line here and this one here and copy it down a ways.
No, I think you want to copy the line below.
This one?
That should click. I don't think that.
So the second one.
Yeah, what is that? Is that
Line 43 or line 4?
that doesn't have the crustal recycling, does it? No.
Not yet.
Yeah. So if you copy that down, and the
Yeah, this one has it. So this line here, line 44, if you just copy that whole line and pull it down, you can basically move where recycling starts going back into the mantle and see what that does to the dots on your plot too. So obviously all these things affect where the dots end up. So another way of saying this is finding a unique solution to this problem is quite hard.
It's a nice illustration of the data null space, the data that you will never get rid of.
Yes. If you were to try and invert this, there would be a lot of solutions probably.
A lot of bad solutions.
Potentially. Whether you know they're bad is another question. All right, so if everybody's done playing with this exercise, is that right? And is everybody ready to move on, or are you still working on moving dots around? Satisfied with your dots? Okay, good. All right. Okay, so that was the dots exercise. All right, so the point I tried to make a little bit ago already is in order to explain the fact that we have much more spread in the data than the two dots, you probably have to generate more reservoirs. Another way to explain like the trends we talked about this morning already in isotope space is you can mix things. If you have two different melts and they have isotopic compositions that are different, you can mix them together. And you can get trends by mixing different proportions. So that's what I'll talk about next and have you play with. So mixing. Simplest case. I have two batches of melt. Same concentration. In this case, we'll do strontium. Same concentration of strontium, but different isotope compositions. So one is blue, one is yellow. We all know that makes green, right? Very simple. That's just the average. So if the isotopes are in this case, strontium 8786 is 706 and 703. By mixing them, I just get the average of the two. Simplest case. How can I make it harder? I just hear mumbling. Different concentrations, yeah. So usually the concentration of the elements for which you have isotopes that you're measuring or interested in are not going to be exactly the same in concentration. So I have to adjust for that. I have to count the atoms basically from both melts to come up with what the average will be. Right? So in this case, now I have lost my laser. Now I have granite at say 900 ppm strontium concentration and the ratio that we had earlier. And this has a basalt but maybe 300 ppm strontium. So then I have to balance it by saying, okay, here's the two isotopes, and you just balance it by 900 out of the total, 900 and 300 versus 300 out of the total. That gets you a mixture of the two weighted by the amount of strontium in both melts. All right, so this is just using the concentrations to balance the mixture out. Not very hard math yet, right? All right, what else can I do? This assumes a 50-50 mix. That's not necessarily true, right? So I can also add different proportions of each, right? If I take a hint of basalt into a large amount of granite, or the other way around, this is a hint of granite. Well, 20% is more than a hint, but a smaller amount of granite in a larger amount of basalt. This scenario would be, for instance, if you have basalt coming into the crust, it might melt some of the granite, might melt some of the granite or other country rock with a similar composition, and you would get something to this effect maybe. So 900 ppm and the strontium isotope signature, 300 ppm the strontium isotope signature, and two different proportions, 20 versus 80. So now I just take the same amount, the same formula as I had before. I just add the proportions of the two to the equation as well. So you can just write that out in a more generic case. The mixture, the ratio of the mixture, fraction of one times its concentration times its ratio, plus fraction of the other times its concentration times its ratio. We can do that not just for one isotope. I can obviously do it for all the other isotopes as well, right? So when you're doing mixing kind of things, you want to make sure that if you're going to come up with, I need 5% mixture, for instance, what Matt was saying, in order to make this Samoan lavas, I need maybe 5% continental material added. Well, in that case, you would want strontium, neodymium, and whatever other isotopes you've measured all to indicate the same percentage roughly. So the strontium of the mixture, the neodymium of the mixture is exactly the same in both cases in terms of the fraction of the one strontium component and its concentration. The fraction has to be the same for the neodymium. The concentrations can be different. And then there's the second component, same fraction F2 for both of them, right? Because it's that 20 versus 80%. I'm adding 20% of granite. That means the 20% granite goes for both the strontium and the neodymium and whatever other isotopes. So fractions are going to be the same across the different isotopes, but the concentrations and the isotope value, the ratios are going to be different. All right. So where does that go next? It goes next to what happens when you make these kinds of mixtures on a plot. So this is a generalized plot, but basically this has two isotope ratios on the axes, and a basalt and a granite. And it turns out that it matters what those concentrations look like between the one component and the other. So all these different curves are different possible mixtures or mixing curves. So if I'm at this point here, I have 100% basalt. If I'm on the other end, it's 100% granite. So where's 50-50? Well, it depends on the concentration, but it's going to be somewhere in between. And basically, it could be a straight line, and it could be a curved line, a hyperbola, based on the actual concentrations in here. So it turns out that it's all dependent on the neodymium and the strontium. If we go with the neodymium strontium like we were doing in the previous slide, it all depends on the neodymium and the strontium concentration ratio in the one component versus the other one. So these concentrations determine whether it curves one way or the other, or whether it's a straight line. The isotopes determine where in isotope space this mixing array ends up. And so the idea is that if you have a little trail of dots in your isotope plot, you may be able to fit a mixing curve through that little trail of dots that basically just describes, okay, I need to have slightly different proportions of the basalt and the granite, and I can describe a small range of mixtures that basically explain that data. All right, so we're going to play a similar game to what we just did with the dots, but now it's with a mixing exercise. So basically, actually I'll just go and look at it in Excel. It's probably easier. All right, so what I've done here is similar to the previous exercise. That same plot's here again, right? Here's my plot of neodymium and strontium. Here's a lead-lead plot. I've also added a strontium to a lead plot. And so now we are going to start with a couple of compositions that I've kind of based somewhat on what we were doing just now, some estimates of what the mantle and the crust roughly might be in terms of strontium, neodymium, lead, and 206 and 207, 204 lead compositions. So these are numbers that are estimates. You can play with those. You can change that around a little bit. Obviously, these are the endpoints of that mixture, so they anchor where the blue line starts and ends. And then here's those concentrations. So the concentrations are the thing that are going to control how curved this line is going to be and whether it curves one way or the other, right? And so the exercise now is going to be, can I explain the majority of ocean island and mid-ocean ridge basalts here into the crust by mixing through here, and does that same mixing set of variables also work in these other isotope spaces? So I'll just show one example. I have for strontium here, I did for the mantle, this is a primitive mantle estimate, and for the crust, this is sort of the average crust composition as a starting point. So say I had only a tenth of that amount of strontium, that substantially changes the curvature because I now changed by a factor of 10 the concentration of strontium in the crust, right? And so you can see how some of these things are going to be pretty sensitive to what you are looking at. All right, and then I had a few goals. Oh, well, you don't really need to see that it's connected to a screen. That should be better. All right, so some of the things to try. The easiest one is to try and make this curve, this blue curve, fit what's called the mantle array, sometimes the mid-ocean ridge and the ocean island basalts. So that's one exercise. But then the second part is, once you've made that work, check the other plots and see if your solution for this also can work for the other isotopes. And then particularly the strontium lead plot, the bottom right plot, you'll see is going to be a little tricky to make a mixture of Morb to EM2. EM2 being sort of the most continental looking thing in the hot spots. Also in the zip file, for those that don't like Excel, there's a MATLAB script that you can do the same thing with. I didn't put all the background plots in, but in one of them there's a background plot. And so if you like MATLAB better, that's another option to play with.
EM2 is shifted pretty far to the left.
Mm-hmm.
And I mean, I can easily
Well,
change the curvature, right? But
if you look at the
value.
If you look at where it goes, the crust goes to 0.725, and then if you look at where the plot actually cuts off, so it goes way out here somewhere, right? And so
I gotcha.
You have to either change the curvature substantially to start following that trend, or you have to move the lead isotopes of the mixture to make that mixture work.
Got you. I didn't look at the strontium value.
really underdo the strontium concentration, or you just have to move the lead over to start the lead isotopes in sort of a FOSO-like composition. Otherwise, it's just, you're never going to get there otherwise. But then this obviously ends up becoming very small. I mean, and that's essentially that's what Matt did, obviously, right? Is to make this thing work all the way out to 0.72.
Right.
His mixture is some sort of middle of the road.
Instead of crust, you could pick a sediment.
Right.
And changes, still the changes to FOSO. So we could make this one 19.5. Oh, I see. And we can move this maybe up to 19, just a round number for FOSO would be about 19 to 15.55, like that. Now, yeah, see,
Yep.
that's good. Should we actually
You might want to be a little bit higher in 7.4.
way up there? Yeah, that's sitting at the EM2 grade.
All right.
So this means it should also try to describe a curve or more or less the same trend as these two blobs, right? It should.
Well, yeah. So you still want to have a crustal and a mantle component. So your mantle blob should still be within the mantle blue-ish colored blob. blob somewhere. And then the crustal component should be, since EM2 in this case is upper crust, it should be in this green thing somewhere.
So I should like.
I don't know which one is which, but yeah, it looks like yours is reversed. So then you can start playing with these two. The lead isotope compositions that you start with can be slightly different, and you can move the starting or the endpoints of the curvature of the curves around a little bit.
And this, because this one, it's like.
Yeah, now you're going this way, so you want to probably have your crystal component have a slightly higher 6.4 and your mantle a little bit lower. So you probably want to change the 206, 204 of these two. I would probably switch them. Okay. So I have 18.8 and 1915 instead of 1915 and 18.8. So I would switch those two left to right, and then it'll switch this around. It'll be closer.
The initial crust values were there from Nick and Gal too?
No. No, those are just read off of these plots, pretty much.
Okay. Thank you.
Now these are concentration estimates. Those folks, neither of those two papers try and do the compositions. They just are, in terms of isotopes, they just do the trace element and major element ratios. All right, so I presume everybody's been able to make the blue line curve through the mantle array by just playing with the strontium and the neodymium and the parent rubidium and samarium values. Is this correct? Everybody was able to make this curve about right? So the second part is, does it work in the other plots? Right? If you make this curve too much, it might make it work here, but it's pretty hard to make some mixture of these blue dots. The blue dots are the mid-ocean ridges. And then this EM2, which is sort of continental material, we think to get along this array of dots, get a mixing array there, you really had to move the mantle lead composition over a little bit so that the line actually matches the dots and actually seems to fall along those isotope values as opposed to sort of crossing through them. I don't know whether you guys were successful in doing this, but you have to sort of start playing with the actual isotopic compositions of the endpoints to make that shift so that line actually starts moving over, right? In this particular array, there's not a lot of dots that really curve over towards the mid-ocean ridges, and you really sort of have to go almost straight up. There's a few hot spots that kind of form a bit more curved fields on the other side. And so in those cases, you can actually play with and make fairly extreme concentration ratios to make it curve. But in a lot of cases, these things are pretty straight. And so you can't really make it curve too much. That would then, if it curves too much, then it wouldn't necessarily follow the actual isotope data you're trying to explain anymore, right? So the next thing is similar to the previous exercise, is if you make one of these things work, is then you can start looking again at your values that you've put in, the isotopic ratios in the top over here, and concentrations you put in the second block here, and go back and think about whether or not those are actually reasonable numbers. So since I started with, for the concentration, since I started with somebody's estimates of what particular mantle and crust values could be, I now modified those a fair bit. Then you have to start thinking about, is that reasonable? Is there something crustal that could look like that? So that's always going to be an exercise when you do this kind of thing, is normally speaking, what you would do is you'd say, okay, well, what two components do I have that could mix? What are their compositions and isotopes and concentrations? And then see if the mixing curve looks about right. In this case, we're going about it the other way, more or less, and saying, okay, if I mix these two things, does it explain anything? That's usually not the approach people take. But if you push it enough, you could do this. So it turns out, in order to explain this trend to EM2, you have to sort of start more in the middle. You have to move your 206, 204 to the right a little bit. So that's what this did here. And you have to move the actual crustal lead 206, 204 over a little bit as well to make this sort of still be reasonable in lead isotopes. And it turns out if you look in Matt's paper where we looked at the EM2 compositions, he has a model that basically starts with something like this, a composition like this, out to upper continental crustal compositions. And so you can actually go through the exercise not just with the isotopes, you can also look at the trace element patterns of, okay, I can, for each dot along this trend, I can see where it lays along this blue line and see what the fraction of crust versus mantle is that I need to explain that dot. Then I can also look at the concentrations of all the trace elements and see if I mix those two, if it actually looks like the rock that I have or not. So there's a number of checks you can do sort of related to the same exercise to see if what you've actually come up with is a reasonable fit. The most important thing that you need to think about with this is if you're going to do a mixing calculation to explain your data, it's got to work in all the isotopes. And I think particularly earlier on, people used to have just one or two isotope systems in their papers and explain their data with a mixing model. But then you add another isotope and suddenly it doesn't work anymore. You need a totally different fraction of one or the other component to explain it. So this is always something to think about when you're doing this kind of thing, is it has to work in all dimensions. In all isotope dimension, it also has to work in the trace element dimensions. All right, I think I had one more thing to ask in the PowerPoint. What was the last thing? Oh yeah, so what needs to be changed the most to get this morph to EM2 array? So we sort of talked about this already. So what do I need to change the most to make this array here work? If I change the concentration data, the strontium and the lead data, it curves, but then it doesn't really overlap anything but morph compositions here. So the bigger shift to really make it work is really in the starting point in the isotopic composition of the endpoints, right? All right. Now, one more thing to think about. So I think in the title I said something like straight lines versus hyperbolas. So these things are curved. This one is much less curved because all you're looking at right now is a small part of it, right? Our crustal composition goes up to 0.72, so that's like a way out here somewhere. This curves very gently. How about lead isotopes? Looks pretty straight, right? So the whole exercise in mixing, the curvature that you get depends on the concentration ratio of the two elements that make up the isotopes that you're looking at in component 1 versus component 2. So can lead isotopes, if you're doing a mixing exercise, can you ever make lead isotope mixtures curve? No. Because? It's all the same lead, right? So here's our ratios for lead that we measure. They're all part of lead. So They all divide by 204, which means we're all just interested in the concentration of lead. So in terms of the curvature, neodymium over strontium, in this case, it's lead over lead in the one component versus lead over lead in the other component. So R is always 1. It's always a straight line if you're mixing in lead. And that's not just lead, any isotope system. So if you're doing stable isotopes and you're plotting iron isotopes against iron isotopes, any mixture is going to be a straight line too. Right? So that's the fun part with these isotope systems is you always have to think about if straight lines have a meaning. I already showed you there's another meaning for lead to straight lines if you are looking at the 206, 204, 207, 204, since they're both generated from uranium decay. If I, at some point in the past, start, let's see if I still have that open. I do. So if I, at some point in the past, start taking off a small amount of melt, and I end up making a different curve coming off of whatever normal Earth evolution curve comes off, I end up on a point that is on the same line here. Basically, you grow in on a curve, and that ends up defining a line. That line is effectively the age of this event. So if you see a line in lead isotopes, there are two options, actually. It could be an age effect, where the melt versus the solid residue that's left behind have different amounts of uranium to lead, and they end up on different points along this line. Or it could be a mixture. So with lead, it becomes a little bit of a harder task to interpret whether or not a line or a linear trend is actually a mixing trend or an age effect. So in that case, you want to probably look at some of the other isotopes as well to make sure that whatever you choose is the best for you is actually what's going on. All right, that is all I have for this exercise. So the mechanics of the mixing doesn't really change. So what I gave you in the spreadsheet and in the MATLAB script is just basically the simple equations to do this. And so you can replace it with any other isotope system, as long as you put in concentrations and isotope ratios, it'll work. This is not very hard by any means. The hard part is to come up with a mixture or a curve or a straight line that actually makes sense with your data and that actually has a meaning in terms of the two things you are mixing together. Can you actually mix a certain crustal composition with a certain mantle composition to make this work, for instance? Or if you're looking at a volcanic system on a continental crust and you're interested to see whether the small trend you're seeing is crustal contamination, can you make a crustal contamination mixture between what you think is the upper crust or the lower crust, whatever you think is mixing, and the original melt? Those kinds of questions you can play with. And it doesn't really matter what isotopes you want to use. You can do the same exercise, just replace the isotopes and the concentrations with the relevant ones for your problem. All right. As I said, that's what I have. Yeah?
This is probably a very naive question. How do we know the initial lead concentration?
That's a good question. That's actually really hard because lead is volatile. And so we basically have to do a lot of hand waving and then say we think we know roughly what lead is. But that's one of the hardest to constrain. That's why people really like working with things like samarium neodymium, because presumably we got at least most, if not all, of our chondritic amounts of samarium and neodymium. With uranium lead, it's much harder. You can, as I showed in the other picture, in here, we have some idea what the solar system starts out in isotope space. because you can look at metal meteorites and look at non-uranium bearing phases, get the isotopic composition. So do you have the starting point? But that's already that's a fractionated meteorite, right? So it's not the best. But that at least gives you an idea of what we started with. But the concentrations are much harder. I don't know, Bill, have any idea? No. It's mostly a lot of if this then that kind of constraints. You can make estimates based on a variety of relationships. I think the cerium-lead kind of relationships are things that people rely on. Like if you have similarly compatible elements, then you can extrapolate. So cerium and lead behave similarly in melting, and cerium behaves much more nicely during condensation than lead would. So you can play those kinds of games to get some idea of what there should have been, but then how much did we lose? So you mostly have to work backwards, basically. You know what you can measure in rocks today and go backwards from there.